Let's start. Hello, everyone. First of all, thank you for this who are offline and online. We from Data Science Society decided that now each week we will going to give a chance to each team present its results, and especially go in the details, because what we find out that for 3 minutes it's not realistic to show anything what you did, and I mean a part of your masterpieces. Also just want to give you an update from the Data Science Society. What we are planning in late April to make the one similar to this datathon. It's called Academia Datathon. This Academia Datathon is focused only mainly and particularly for the students and the way they apply their practical knowledge. We will currently we have agreement from more than 5 universities from Bulgaria, 2 from Croatia, and we're in discussions in Greece, Hungary, Austria, and probably Malaysia. I have a call tomorrow, so probably we will know how many and which university are going to participate. The main idea here is that there will be only one case. We are discussing directly with the professors, so the idea is that professor will be mentors, and all the students can work in various teams with some of their colleagues from a different country, and really practice what they learn, and we believe that they will learn a lot. Also, after that, we are in discussions to make another datathon, which is going to be especially for text, and it's NLP, or we call it fake news. We are still in discussions which company is going to participate, and still it's an idea. It is planned to be June or later, somewhere there, June or July. Something what we find out now, something what I can share for the datathon, for the online datathon, that we were so happy that at the end the final was. I mean, the audience was not only offline, but from online there were more than 500 views from 50 countries. What we saw also a huge interest of the articles which the teams created. Also, probably you have heard 38 teams submitted their first intent to participate. At the end, there were 28 results, and something which we saw that within 5 days there were 5 or 6 more articles uploaded. Even for one of the cases which we didn't have a team, there was one solution. As a next step, apart from these datathons which I mentioned, we also plan to start promoting the data chat, and people get and start having more information there. Some of the cases groups will be closed, and we will open this SNA, which is for social network analysis, machine learning, and different kind of groups, so people can start using it. Also, if you are already in the data science platform, you can also install a mobile app, so everything, all people can work, and yeah, you can have it on your mobile in terms of notifications. And video conferencing also is going to be there. So here we are testing this part, video conferencing. So I guess everything will be working. Everything will be at the end stored on our YouTube channel. The idea here is that every week we will not make an offline. There will be once per month offline event, and all the others should present it online in the platform using the video conferencing. What else? The sponsors. Yeah, I forget about that. So we have thanks to Telenor and Receive-Bank, so they are supporting us outside of the datathons for this kind of meetups, having the beer, having the place here, and being able to stream the event. So yeah, thanks again to Receive-Bank. and Telelink. And now is the time, as we spoke, each team will have the opportunity to present their case and go in details. So one of the finalists is the TROL team. So they were also a winning team from the audience. And I was also partially involved in what they are doing. So I'm also really curious what they did. So expect questions. So the floor is yours.
Okay, hi guys. That's the team. We are Team TROL. We are kind of back at the stream.
Oh yeah.
About a minute. So we are Team TROL. They have T-shirts with our team. You can totally check it out in internet. But at first, wait for the end of the presentation. So you maybe don't want the T-shirt after all. So we were working on the case about the SNA at that datathon, and the case was pretty simple. We had a graph representing calls from users, and those calls were made from a Bulgarian telecom, and the graph was looking something like about that a bit later. First, we had two tasks about that graph. First, find something interesting and useful, and second, satisfy the tasks that were given from our business mentors. And those tasks were to define two membranes at the graph and to define the leaders in the membranes and the core of the graph. The core is the rest of the graph, which is not membrane, of course, and all of those leaders are at clusters, so it would be nice to define the clusters. And after a while during the hackathon, like the second day of the hackathon, we received predefined leaders, so we can check results and we can solve the last task, which is to define the strength of connection between all nodes in the graph to the group 5 of the leaders. So the structure that we received was looking like that. That was our domain knowledge. Our mentors from the Telecom here in Bulgaria came and told us, okay, the graph is structured like that. There are two membranes and there is a core, and the big dots on that picture are actually the leaders that you're looking for. And when we saw this picture, at first we were very happy with it. We were like, okay, we can see everything. Everything is on that picture. So cool. But then we were starting to think about it, and does anyone know at all what a membrane in a graph means? We didn't. We asked people around us, and they still didn't. So we decided to do what we do best. We Googled, and as you can see the results from the Google search, there is a lot of biology about membrane and nothing about computer science, which made us a bit confused. So now we are a bit like, oh shit, we don't know how to solve that task. And we did what we know how to do, and it was, let's do some statistics. So we started to check out the statistics of the graph, who called who, how many times, and in 5 minutes, a colleague of ours, he was not on our team but was working on the same problem, told us, dudes, in this network, people were talking only to their moms, and this was like the thing that led us to the right way. It was actually true. A lot of the nodes in that graph had only one call. And we decided, okay, a lot of them had one call, but at the graph there are like 1 million and a half calls. So maybe some people called more. Let's check out how many outgoing and ingoing calls all the people in the graph have, and then bang, we have this. We were so excited, so strong correlation. We have outgoing versus ingoing calls at correlation 89%. And we were like, this is so amazing. Oh my God, we have done the breakthrough, but this actually doesn't tell us a lot. And after a bit of research, we found out that actually this is considered normal at the phone call networks. Most people had as many outgoing calls as ingoing. And at that picture, you can see something else, but at first you're blind because of the strong correlation. At that picture, there are a lot of outliers, and some of those outliers are having zero received calls or zero outgoing calls, which is pretty strange for a normal person to have. So we decided to do some kind of different statistics. I'm not sure that you can see the table, but what it says is at the graph there are almost 18,000 nodes that are covers only, so they have never received a call, and there are more than 64,000 nodes that have never made a call, and there are, of course, the nodes that have both received and made calls, and those are only 35,000. And these statistics made us think, okay, we see the membranes actually. Cores only are the first membrane, and receivers only are the second. So the core could be the users that have communicated like a normal person, have received and done calls. So, okay, now comes the question. How do we decompose the graph? And to decompose the graph, we need first to do some statistics about the membranes. So you can see here that 15% of the nodes are in membrane 1 with the cores, and only 1% of the nodes are there because the unique cores to that the unique receivers of calls from that membrane are not that much. Same is happening here. The receivers are a lot, but those receivers were called only from around 2,000 users. Those 2,000 users at the first membrane and the second are different. We've checked that out. It would be pretty convenient to be the same, but no, it is not true. So now, a bit more statistics here. You can see the core contains 30% of all nodes, but 69% of all edges. So actually, the interesting codes are in that core that we've found. And now, the correlation we've told you already about it, and yes, that's the article that you can check out. Why it's normal to have as sometimes happens, to have this strong correlation. So now we needed to decompose the graph, and it was pretty obvious how to do it. Just take the two membranes and remove them from the graph. But after like 5 minutes of thinking, we were a bit confused. So if you remove all of the cores, then some other nodes could be again cores only because you stop some people from receiving calls by removing the others. So actually you needed to decompose the graph recursively, and we've done that. And actually we've done that like for 15 minutes, and we were not sure if we are not building a small Death Star. Are we doing it overcomplicated? So we've done the algorithm about the decomposing for about 10 minutes, and we argued about it like an hour to see, okay, is that needed or not? We are still not sure if it was needed because the graph decomposed itself without the recursion. You just take the two groups and that's it. But, well, we've done it. So we have the first task solved. We defined two membranes and we found the core of the graph. And now would be a very good time if there are some questions about the first part of our job. And if not, you can always ask me later. Okay, so let's define the leaders. Sounds good, but on the other hand, we have very strange membranes with a very unusual structure. And usually when you do data science, the unusual structure data is interesting. So let's analyze the membranes. What do we have there? First membrane is tree structure, the cores, and the ones they've called. After fast analytics, we've seen that there are 979 connected components, and one of them is huge with a lot of nodes and looks like a standard code center or code centers. So a lot of numbers calling a lot of other numbers, no visible structure, no visible pattern. The rest of them are pretty strange, and they're strange because they usually call 1 to 3 unique numbers. So imagine you have 100 numbers, cores only, and they go at most one number, only one. So those numbers can be defined as a gateway. The gateway is familiar from computer networking and some other scientific fields. So we found unique gateways, 891, and they were pretty interesting, but we still didn't know what to do with them. But remember that we found it because we find out it's really important if you are a gateway or not. So now you have a covers only. This could lead to a fraud. So imagine you buy a SIM card, you don't register it anywhere at some countries, and you decided to blackmail someone. So you buy like 3 or 4 SIM cards, and the whole life of those SIM cards is to call 2 or 3 users, tell them something, make them pay you or make some fraud with the SIM cards. And it's really easy to match patterns on those membranes. And such patterns were matched, such patterns were matched like that. And this is not necessarily a fraud, but if we have those patterns, some of them should be checked out. More interesting are, on the other hand, the fraud patterns in membrane 2. Those receivers only are usually a prepaid phone, premium rate telephone numbers, and it's really easy to launder money through them. So you just buy SIM cards with your dirty money, and then you call your own premium rate phone, and bang, your money are now clean. And okay, there are some frauds at that graph. And as you can see, okay, this is a bit suspicious, but maybe it's nothing. This could be, worse. Maybe should we check it out, but that is a bit too much. So at that graph were some non-fraud patterns, and we decided to just show a few examples from them. It's really easy to extract them, and with extra domain knowledge, it could be leading to a system against fraud that could be very useful at some fields. So now, okay, the core, we have a task to do. Let's check out the core. It has 30% of all nodes, 60% of all edges. And you still cannot see the table, but it says that it contains 98% of all leaders in the core and 94% of all edges connected to those leaders. So we are on the right way. And some statistics, most of the nodes at the core were calling 1 to 3 receivers and were called by 2 to 3 callers. But if that's not true, then probably it comes the leaders. So how we define leader in a graph? We need a centrality measurement, and it's pretty popular in graph theory. And we decided to try 3 different ones: in degree, out degree, and eigenvector centrality. In degree and out degree are trivial. It's just the number of calls you received and made. And eigenvector centrality is a bit complicated, but it actually shows who are you connected with. So if you are connected to the most popular people in that graph, you would be the one with the highest eigenvector centrality. And we decided to check out, okay, let's take the highest value for each node on those 3 metrics and see how we guess the leaders. We already have the leaders. And
explain a little bit about in degree, out degree.
Okay, yes. So you are a receiver, you are a node at that graph, and there are actually edges going into you. Those are calls that somebody made to you. They are labeled as low, high, and medium. Those are the intents or the importance of the call. And same is for the out degree. The out degree are the calls that you maybe have committed a mistake, not sure. So the in degree are the calls coming to you, so the received calls, and the out degrees are the calls that you made to someone, and they're still labeled with high, medium, or low label. So you know if you have done a highly important call, a medium important call, or maybe not an important call. We are not sure because the data is confidential. We are not exactly sure what does low mean. It could be low like a short call or low like a low connection or something else, but those labels are ordered and we can use them as we want. So we decided to try those 3 metrics, and we decided to guess if this has a high centrality or if this has a high out degree, is that a leader? So we built a ROC curve, and we were pretty impressed. At first, we were pretty sure we'd drawn the ROC curve the other way around, but after a while, we actually realized that's the ROC curve. So both of our three metrics were totally not working. That's personally the worst stroke curve that I have ever seen. And yeah, well, we were not on the right way. So we decided let's keep it simple. We are again making a Death Star. This is too complicated. Let's figure something out that is not so complicated. Although those three metrics was not really the complicated thing in our task, but come on. So what is more simple than that? How many unique neighbors at distance sense and you have? So how many unique people do you know? With how many unique people have you talked to? And bang, 85% precision and 83 precision in a code just by picking the best at that one. So in our group, most of the leaders are the one that have talked to most people, and we were a bit happy. Oh, we are solving the task. We have real results. And then we decided, let's go further. Let's apply a decision tree to that, and we find out that with a just simple decision tree about the unique connections, we can trade a bit of precision about a bit of recall. And then we were like, okay, we can do better with supervised. Let's define a few features. There were like 10 features, and the tree was pretty simple. I don't know if you can read it, but the tree has a 93% precision, and it literally says if you have a lot of unique connections and more than 25 high outgoing calls, you probably are a leader. And if not, but you are a gateway, you're still a leader. So pretty simple explanation. Gets 93% of the gets 89% of the leaders, and it's pretty precise. So this could be improved to a higher precision and recall, but the point here is to see the description of the leaders. So that's literally the description of the leaders in our group. And we were happy about it, so we decided that we are ready to continue with task 3. And task 3 was to define the clusters. And we thought about it, the leader clusters, and we think, okay, Death Stars are not actually a bad thing. They were very cool in the movie. So could we, just build them? And we decided, of course, to build them. Weighted no indexes matrix for density-based clusterization with dbscan. Or with just simple words, we tried to apply dbscan on this is a density-based algorithm. So we decided to define our metric, which says how close are nodes in graph together, and apply it to the graph and find the clusters. So here comes the slide. Oh no. Here comes a slide with a lot of explanations that you probably don't want to read. That's the metric. Let me try to explain the metric simple, because it was actually not that over complicated. So if you are a node at the graph and you are connected with another node, the path between you is exactly the sum of the weighted sum of the edges between you. So if we have 3 high calls and 2 medium calls and 1 low calls, we gave the words meanings. Medium is, I think, 0.1. No, low is 0.1. No, sorry. High is 0.1, medium is 0.3, and low is 1. So you calculate that measure if we have edges between us. But if we don't, the path between us is the number of common neighbors and the path between us to the common neighbor and the common neighbor to the other receiver. So the metric is actually not that complicated, just looks a bit of complicated, and we applied that algorithm. And those are the numbers that I was talking about. So we applied that algorithm, and we were expecting to receive clusters, social groups with one mutual friend. So if me and George are friends, all the friends of George could be at my cluster. We received clusters as usually when you do unsupervised, but they had a, let's say, not bad silhouette coefficient, but they have absolutely nothing to do with the leaders that we were dealing with. So I remember a friend of mine trying to find a metric in scikit-learn that was telling that we are doing good, and none such existed. all of the metrics was saying no, your clusters doesn't part the leaders as they should be parted. So bang, we find some clusters. Maybe they deserve further analytics, but we are not going that way because we are not solving our task. So we decided it's graph theory time, and our favorite part in graph theory was weakly connected components because they were pretty good working at the membrane one of the cores. So we decided, let's do this. That's a weakly connected component in graph. Check it out in Wikipedia if you don't know the definition. It's nothing hard. It's just, let's say, a subgraph in the graph that is connected. So we decided to decompose the graph like that. First, we had the whole graph, and we decided, let's find out all weakly connected components. And the magic happened. We have two components with exactly one leader, which is in the core, and on the other hand, we have 7 another components weakly connected with exactly one leader in each one. And we were like, okay, this looks like it's working, so let's find out, can we make another? But to make new weakly components, we needed to cut some edges. So we decided to remove all the edges that has low value. We removed them, and new more components appeared. And the cool part about that is that each new component has exactly one leader, and usually that leader was, and maybe always, I'm not exactly sure, but usually that leader was the center of the subgraph. The center of the subgraph is the node that is at the same distance from all nodes. This was pretty impressive. It literally looked artificial, like we made it up, but it happened. So we decided to continue removing edges, and we removed all of the medium edges, new weakly connected component, most of them with exactly one leader. There were not a single one group that has more than one leader, which is pretty cool. So we were left with only high edges, and we decided to, let's remove all the connections between two nodes if they have, let's say, only one high connection, then only 2 high connections, and so on. And at the value of only 60 high connections, we had actually 431 connected components with one leader. We had some unstructured nodes just in one big component or in components with no leaders. And when we add those are the groups clusters. And when we also add the clusters defined by the gateways, because let's admit it, if you are a gateway and behind you there are like 100 numbers, that's an obvious cluster. So we were doing like 600 clusters with one leader in the middle, and that's not a cluster for each leader, but it was pretty impressive. So graph theory is working good here, so we decided to do something cooler with that, and a friend of ours, Sergey, also gave us some advice about that. So we decided, let's define component families. Well, at first we were thinking about, okay, a click in a graph, that's a part of the graph that everybody had code everybody. But seriously, how often does that happen? Still, we found clicks, that's a click. It really looks a bit of too much cause, but it usually defines a strongly connected structure in a company in the case of phone calls, because all of the people in your company had call the other people. So if you have a clicks in your call graph, you should totally check them. They mean something, but they are not really interesting. The more interesting part is enclan. You can see the definition again in Wikipedia. It's not that hard. That's an enclan, and it looks a lot like a family or a close friends calling to each other. That's another enclan. So when you have that pattern in your graph, you should take it, you should apply some domain knowledge and some supervised learning, and you should decide, is that a family or is that a group of friends? And this could bring you a lot of business knowledge. You can give offer to those people about maybe cheaper costs or a lot of other things. So, okay, the group 5, that's the last task that we had to do. Yeah, we've done the task 3. We find some clusters. Not all the leaders had clusters, but most of them did. So we are happy and we are going to the last task. And the last task was to define the strength of each node, the connection of each node to the group 5. And the domain knowledge that we knew about group 5 was that they are the bad guys, they are the fraudsters, they are actually the seed words. And we really needed to find a connection between them and to say for new users, are you connected with them or are you not connected with them? So we had not enough domain knowledge to make any assumptions. So we went 2 ways. The first one was to define the closeness between outside through a graph theory. And so this metric that I'm describing here is just the reverse of the shortest path length to some node at the group 5. And if we think about it, that's showing us something interesting. So let's imagine that group 5s are drug dealers. Oh yeah, and let's imagine that you want to know how close your kid is to contacting a drug dealer. So if he has contacted it directly by the phone, the drug dealer, the distance would be 1. If he has a friend that is calling the drug dealers, then it's 0.5, and so on and so on. So these metrics can reveal in such graph, let's say, the drug dealers and their clients. That's how we can use that. But we were thinking, okay, if those are drug dealers and we can define them and their clients, but we know only 2 people are drug dealers, can we define more drug dealers? To do that, we needed to do supervised learning. But first, that's the distribution of the shortest path for all nodes in the graph. And maybe some of you could look at it and say, okay, this might be normal distributed. I've done that. I was optimistic. And then we've done a statistical test. And you probably don't see the numbers again, but the statistical test says, are you crazy? It's so not normal distribution. Like, that is too huge. So, yeah, statistics works in a mysterious way. So if you have to remember something from that presentation, don't look at the graphic and say, oh, this looks normally distributed. It never looks normally distributed. So let's continue with group 5 supervised. We had the features and we decided, boom, let's do supervised. And this actually describes group 5 against all of other nodes. So that decision tree, pretty simple, gives us, am I group 5 or am I not group 5? And as you can see, group 5 are usually with a lot of unique connections, but a lot of medium calls, but not that much unique connections. And if they have less unique connections, they usually have less high ingoing calls. Okay, that does not make a lot of sense, but still we have no other domain knowledge in the graph. So that tree actually, here comes the confusion. That tree has a pretty good confusion matrix. You probably don't see it because my numbers are small, but it has only 3% false positive rate and 70% true positive rate, which is impressive for a tree with only depth of 3. And so let's think about that metric. That supervised metric, if we use as a metric the probability from the decision tree to be group 5, this gave us a metric to, are you a drug dealer in the context that I was talking about. So if the probability from that tree is high, you probably are like group 5. And if you want to know, are you connected with group 5, you can use the first metric that we defined. So now, it's wise to use that metric, the supervised one, because it can reveal bad users just by their behavior. And we've solved all the tasks. And we were happy about it, and we've learned a lot. And some of the things that we've learned are that, first, graph theory is awesome because it worked for our tasks and it worked pretty good, pretty amazing, I would say. Unsupervised learning is hard because when you do it, you need to have a hypothesis, and often you have the hypothesis, you do it, your hypothesis is wrong, you are sad, but you have to keep going. That's how life happens. So Occam Razor is wise. Occam Razor is a solution. Yeah, it's just a motto that you can say the simplest solution is almost the best. almost always the best. That worked in our cases. We've tried to build a few dead stars. They wasn't really working. So just try first simple things, and if they don't work, make it complicated and complicated, but don't start with the dead star. And yeah, that are awesome. You can totally check out the next one. And for the end of this presentation, at the whole hackathon, I was thinking about the guy. I think he was a Canadian journalist, maybe born in English because he had the accent. And he said something pretty wise about our case. It was just because you've heard that we are 6 hops away from each people in the world, but this doesn't mean that we are really close together. It just means that some of the people are center of the world, and all of us are connected to the rest of the world through those special people. So yeah, thank you for your time, and I'm ready to answer all of your questions, I hope.
Yeah, so if you have questions, I just need to check online. What do we get something?
I have one question. Because I have seen that you export the data in various ways. What is your impression? What is your feeling about the data that the telco real data from the telco system, or it's some kind of fake data, not extracted directly from the system, but somehow manipulated? Do you think, did you see any patterns of the real world in this data or not?
We have a hypothesis.
Can you repeat the question, please?
So the question is, do you think that the data from the Dataton given us from the Telecom is real, or have you seen any artificial patterns in it? Do you think it's a real life data, or maybe just data created only for data? So we actually have a hypothesis how the data is collected. We think they have chosen few users that they know are maybe their private phones or phones of the company, and they just started to collect all of the codes. They made a BFS from the leaders, so-called leaders. They started BFS from them, and they took all of the nodes that are next to the leaders. And so if they have done only that, it would be too easy to find the leaders. So maybe they've put some fake codes, or maybe they have take all the codes also of the code ones. But those membranes are formed because somebody stopped collecting data. There are not that much call centers. There are not that much receivers. So somebody just cut all of the received calls from anyone and all the calls from somebody else. So the data was probably collected artificial. We have some hypotheses. We had a few during the hackathon, and the last one is that the leaders were the starting points, and then just the network were collected at 1 or 2 hubs. So yeah, we think it's not real life data, but the core could be considered real life data at 1 hub. So the core was presenting to us how people communicate just through 1 code or just through codes. Two codes. Yeah, we think so. Anyone else?
There is an online question.
What is there? I wrote it down. So can you reveal more about the different groups? Because we mentioned only group 5. What are the details about the others 4? I guess.
Yeah, they are actually,
because you use them for the supervised part.
Yeah, let me find the statistics. So we had leaders with labels 1 to 6. We didn't know anything about them except that group 5 is good, and I think group 1 and 2 were in the membranes. Not sure about the number, but we know knew that some of the groups are in the membranes and the rest of them are in the core. The thing is that we defined our core in such manner that most of the leaders were in the core because, well, we said all of the cores on one membrane, but all of the cores were calling somebody in our core. So some of the leaders, let's say, could be also in the membrane or the core in our case. And we had no further information about the groups. And that supervised warning that I was showing was actually just, are you a leader or not? So we didn't really use the information. We never found a difference between are you group 1 or are you group 2. The only difference that we've made was are you group 5 or not, or are you in a group or not. Mm-hmm. Because we didn't actually have enough knowledge. We only had the graph and it gave us incoming calls, outgoing calls, and strength of the calls. So it was not enough to make a machine learning to guess are you group 2 or are you group 3. So yeah, we defined the groups like one, and we cannot provide any more data information about them. And the only thing we know is from the mentors which group is found there.
But wasn't there information about each node, like a kind of segmentation, or not? Am I mistaken? Or?
No, there is only for the leaders and in which group they belong.
Yeah,
okay.
Actually,
okay.
only the leaders were.
I was thinking that for all nodes you have like a clustering from one to something.
No, we only knew which are the clusters and that's it. Which are the nodes, the leaders, and you have to find the clusters by your own.
Okay.
So yeah. Go.
Maybe a more technical question, but I could not understand very well the meaning of the distance between the red group and the rest. Can you just explain it?
No need to understand. Basically, you.
Can you repeat the question? Just.
So the question was, what's the meaning of that metric that you see on the screen in the real world, and that's the metric between all the nodes in the graph to the nodes in group 5. So what the meaning of that closeness?
Okay, so for a given node, so for a given node, let's call it V, you find all the shortest paths with every node from this special group 5. And you take the shortest one. That is the